So this video is going to be on two sets of notes. First set of notes is going to be on scientific notation. And the second part is going to be on laws of exponents. But let's first take out our composition book and get started on scientific notation. And scientific notation is a way of writing very, very large and very, very small numbers in a more user-friendly manner. So we're going to say scientific notation is a way to write very large and very small numbers in a more compact way. Sometimes it's really hard to write a number that has a lot of zeros, either after or before the number. So this is a way of writing something in an easier way. So this is going to end up being the product of two factors. And the two factors are going to be the following. First factor is a number between 1 and 10, not including 10. The second factor is going to be a power of 10, okay, is going to be 10 to a power. Now, let me start with an example. So let's say, for example, I had the number 321,500 as a number. What I'm going to do is I am going to be moving my decimal. Okay, I'm going to move decimal until I have a single digit from 1 to 9. So if I'm looking at this, okay, right now my decimal would be right here after the 0. Right now I have 321,500 in front of this. I don't have a single digit. I've got 6 digits. Okay, so I'm going to move it 1 place, 2 places, 3 places, 4 places, 5 places, until I have this number here, this 3, as the only number that's in front of my decimal. Okay, a single digit from 1 to 9 cannot be a double digit. So this 3 is where I'm going to be moving my decimal to. So let me just rewrite this number here. So 321,500. And my decimal really is here. And again, I'm going to move it until I have a single digit in front of my decimal. So I am going to move it 1 place, 2 places, 3 places, 4 places, 5 places, And now my decimal is going to be here. Now, the way I'm going to write this number is I'm going to write this number as 3.215 times 10. And again, I moved it 1 place, 2 places, 3 places, 4 places, 5 places. So I'm going to times it by 10 to the power 5. That tells me how many places I moved it. Okay. So when I times by 10 to a power, I'm really moving my decimal that many places. Okay, so that number is going to be the compact form, the scientific notation form of 321,500. So let's say, as an example, I maybe have a number that isn't really super big, but maybe super small. So let's say I have 0.0000123 as my example. Now, again, I always need to move my decimal so I have a single digit in front of it from 1 to 9. Okay, this is 0. This is not from 1 to 9. So I'm going to move it 1 place, 2 places, 3 places until this 1 ends up in front. Okay, so I'm going to end up moving it until that 1 is in front. So I am going to move decimal again until I have a single digit, and this is important, from 1, okay, not 0, from 1 to 9. So let me just move this up a little bit. Okay, and let me just recopy this number. So I have 1, 2, 3 zeros, and then 1, 2, 3. And again, I need to move it until I have a single digit from 1 to 9. So I'm going to start where my decimal is. My decimal is right here, okay? And I am going to move this decimal 1 place, 2 places, 3 places, 4 places until it is right here. So I moved it once, twice, 3 times, 4 times. Once, twice, 3 times, 4 times. So I'm going to write this number as 1.23 times 10. And since this number is a really, really small number, instead of raising it to a positive 4, I'm going to raise it to a negative 4 because I'm moving the decimal in the opposite direction. Now I'm going to rewrite 2 problems here and have us try these. And before I do so, let me just kind of make a note here. Okay, note. If you saw 25.6 times 10 to the 4th, what you want to pay attention to, is this in scientific notation? Is this a single number, single digit in front of my decimal? No. So this is not in scientific notation. Need a single digit, not a double digit, a 2-digit in front of the decimal. So if I was going to take this 25.6, which is times 10 to the power 4, okay, so really I would move this decimal 4 places to get the actual value. But if I wanted to know if this is in scientific notation, it is not. I need a single digit in front, and that single digit would be the 2, not the 25. That's a double digit. So I'm going to move it one place, and my decimal would now be here. So what that means is this new number would be 2.56 times 10. And it was to the power 4, but I moved it one more place. So now it's actually going to be times 10 to the 5th. Okay, just want us to understand that. Sometimes things look like they're in scientific notation, but they are not. Okay, and just so we understand some vocab here, I'm going to write one column with scientific notation, and one column for standard form. Standard form is how we would normally see the number if it wasn't written in scientific notation. So let's say I have 5.32 times 10 to the power 6. That would be scientific notation. Again, notice I do have a single digit in front, so it is going to be in scientific notation. Now, what does that look like here? So what I would do is I would take that 5.32 and I am going to take that decimal and I'm going to move it 1 time, 2 times, I have to add a 0 3 times, I need to add another 0 4 times, I need to add another 0 5 times. So I'm going to just double check 1, 2, 3, 4, 5. I need to do it one more time, 6. So my number would be 5, 3, 2, 1, 2, 3, 4. I had to move it 2 places, but I still had 4 more places I had to move it. So I had to add 4 zeros on to cover that spot. And that number would be 5,320,000 would be that standard form number. And let's say I do one going the other direction. So let's say I have 3.07 times 10 to the negative 4 as an example. So what's going to happen here, okay, just so you understand, it is in scientific notation because I do have a single digit in front. I'm going to be trying to rewrite this number in its real form, okay, what we call standard form. So I am going to have 3.07 in here. I'm going to move this because I have to go the other direction. So 3.07, and I'm going to move this decimal 4 places. So I'm going to move it this direction 1 place. Have to add a 0, so that's 2. Have to add another 0, 3. Have to add another 0, 4. And then that's where my decimal will go. So this in standard form is going to be, I'm going to put a 0 in front, just in front of my decimal. It's not one of the 3 zeros I wrote. So I'm going to have 0 point, and then I have 0, 0, 0, 3, 0, 7. Now I'm going to add a page for you guys. Turn to another page, and we're going to discuss laws of exponents. So this is going to be laws of exponents. Now, first, I want to just make sure we go over some terminology. So let's say, for example, I have 3 to the power 4. Okay. The 3 is called a base. The 4 is called an exponent or power. Now, sometimes they're going to ask us to write something in expanded form. So what that would mean is the following, okay? 3/4 in expanded form means I'm going to write what 3 to the 4th means. It means I'm going to take 3 and multiply it 1 time, 2 times, 3 times, 4 times. That's what 3 to the 4th means. I'm taking 3, which is my base, and raising it to the power of 4, which means I'm multiplying 3 4 times. Now, when I do that, I'm going to end up with 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. So 3 to the 4th is 81. Now, we are going to be learning some laws of exponents. I'm going to have us expand a couple of problems here first and see if we see a pattern. So I want us to try the following. Try. And I want us to write in expanded form and look for a pattern. Okay, so have this in your notes though. So let's say, for example, I am asking you to do x to the 2nd times x to the 3rd. And so I want you guys to write out x to the 2nd in expanded form and x to the 3rd, and then see if you can count up and see x to what power it should be. So pause the video and try this part. So if I'm writing out x to the 2nd, x to the 2nd would be x times x. If I am writing out x to the 3rd, x to the 3rd would be 1, 2, 3, so x times x times x. Now, if you look at this, hopefully you see that we ended up with 5 of these. We ended up with 5 of these. So this ended up being x to the 5th. So what we ended up doing was we took the exponent 2 plus the exponent 3, and that's how we got the exponent 5. So really, I took the exponent 2, I added it with the exponent 3, and we ended up with the exponent 5. Let's say I have x to the 2nd raised to the power 3. So another way of thinking about this is I really have an x to the 2nd, let me do it this way, times an x to the 2nd times an x to the 2nd, because we have 3 of them. So if we were to expand this, this would end up being, I'm just going to do these in different colors. I get an x to the 2nd here as x times x. Then the next one would be another x times x. And then the last one would be another x times x. So this x squared is here. And this x squared is here. And this x squared is here. Now, what is my final result going to be? Well, how many do I have? 1, 2, 3, 4, 5, 6. I end up having 6 of them. Now, what happened? I really have 3 sets of 2. So what I do with my powers is I really multiply them. I really multiplied 2 times 3, and I ended up with a power 6. I call this power to power. Now, let's look at another one, and then we will write these out official. Let's say that I have x to the 6 divided by x to the 2nd. So what I'm going to do is I'm really going to write this as the top is going to, so I'm going to write off the top as x to the 6th and the bottom in expanded form for x to the 2nd. So on the top, x to the 6th, I would have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. On the bottom, I would have x times x. I would have 2 of them. Now what happens is anytime I have the same on top and bottom, it's actually going to become a 1. So this x on top and this x on bottom really cancel out and become a 1. And this x on top and this x on bottom cancel out and become a 1. And how many x's do I have left? I have 1, 2, 3, 4. Now, what happened? I had 6 of them on top. I had 2 of them on bottom. So that what I want to think about is how many x's can I cancel from top and bottom? How many x's can we cancel from top and bottom? I'm really making ones, but I'm just going to use this terminology. Can we cancel from top and bottom? Well, the answer to that was 2. I could cancel 2 on top and I could cancel 2 on bottom. Then I asked myself, how many x's do I have left and where? And the answer to this is I have 4 on top. So my final answer was x to the 4th. Now, really what's happening is I took 6 minus 2, I subtract them, and I ended up with 4. Now, let's say instead I had it like this, where I had, let's say, x to the 3rd over x to the 5th. Okay. And I was to write this out. So if I was to write the top out, okay, that would end up being 1, 2, 3 on top. And then if I was doing the bottom, I am going to have 1, let me space that better. 1, 2, 3, 4, 5 on bottom. And again, I'm going to cancel what I can from top and bottom. Now, if you're looking at this, you'll notice that I can cancel 3 from top and bottom. Okay, 3 from top and bottom. And how many did I have left? Well, I had 2, but where did I have them? I had them on the bottom. But what do I have on top? I really have a 1 because each of these x over x is really just a 1. Now, if I was doing this, that is going to be my cleaned up answer. But if I was following the laws of exponents that we're going to be writing here in a second, I would have done 3 minus 5. 3 minus 5. It's always top minus bottom. And I would have ended up with a negative second. So what we're seeing here is that this x to the second, 1 over x to the second is the same as x to the negative second. So we're going to end up seeing that also as one of our laws. Okay, so let's officially write out our laws of exponents here. Okay. So laws of exponents. Okay, so the first one I'm going to write is, let's say I'm going to use the letters A times, I'm going to write a one like this, x to the A times x to the B, where I'm multiplying same base, have to be the same base. What I do is I add the exponents. So an example, x to the 5th times x to the 4th would be x to the 9th. I add 5 plus 4. Number 2, if I have x to the A raised to the power B, that is going to be x to the A times B. So an example of that, let's say I have x to the 5th raised to the power of 4. Power to power, I multiply, and I'm going to get x to the 20th. On number 3, if I have x to the A divided by x to the B, that is going to equal x to the, always, we're going to subtract, and it's going to be top minus bottom, A minus B. So as an example, let's say I had x to the 10th divided by x to the 6th. That is going to be x to the 10 minus 6, which is 4. Two others that I'm going to write here. If I have x to the negative 1, that is going to, anytime I raise something to the negative exponent, notice that here, let me grab my spotlight here. So here, when I had x to the negative second, it was 1 over x to the second. We call it the reciprocal. I take the reciprocal of this, which is going to be 1 over it. So this is going to be 1 over x. Now, I'm also going to write that if I have x to, and let me just have us understand this also, that if I have 1 over x, that's going to be the same as x to the negative first. Okay, I can also see it that way. Okay, if I have x to the negative m, where it's any negative exponent here, Here, no, I'll keep it as an m. That's going to be 1 over, okay, the negative makes it 1 over, and it's going to be x to the positive m. Okay. Now, what that does mean, I'm going to do this in a different color, is let's say I had 1 over x to the negative m, where I had the negative on bottom. Wherever the negative is, it's going to end up being the reciprocal. So since this is on bottom, then this is actually going to be equal to x to the m. Now, the next one I'm going to add, the last one I'm going to add is if you raise something to the power 0. When you take anything to the power 0, you are always going to get 1 back every single time. And these are going to be our laws of exponents. So you're going to be referring to these when you're doing the problems in today's classwork and homeworks. It's going to be a very important thing that you're going to want to understand for all of your math career.